This lesson is a review of applications of right triangle trigonometry. There are some things to remember when working with trigonometric problems. Since we are going to use a calculator from time to time, make sure to set your calculator in the gray mode. Also, since trig functions are quite sensitive, use at least 4 decimals when evaluating those functions. For example, to find sine of 32 degrees 10 minutes using a graphing calculator TI-83+, hit the mode button and then scroll to the line radian degree and highlight the degree mode. Enter. Now we know we are in the degree mode. Let's go back, second mode, and enter sine 32 degrees. Remember, the degree sign is listed under angle. In 10 minutes. Again, under angle list, number 2 represents minutes. Okay, enter. We end up with 0.532383 and so on and so on. Obviously, we need to round this number because it's too many digits, but we should round to 4 decimal places. So it will be 0.5324. 0.5324. So you may want to check your calculator. If you've got the same answer, it means you're in the right mode. Next, use the inverse shift or second function when finding angles, and round angles to 1 decimal place. For example, if we want to figure out what's the angle theta such that cosine theta is equal negative 0.35078, we go second cosine to recall the inverse cosine function of the number negative 0.35078 and then enter. The answer is in degrees. We should round to 1 decimal place, so we end up with 110.5 degrees. 110.5 degrees. Okay, what are other things to remember? Apply the Pythagorean theorem only when working with a right angle triangle. So before using the Pythagorean theorem or the SOHCAHTOA rules, we have to make sure that our triangle is a right angle triangle. That's why this section is called right triangle trigonometry. It applies only to the right angle triangle. Also, use exact answers when working with special angles. Anytime we work with 30, 45 or 60 degree angle, we are expected to give the exact answer. Some word problems refer to angles of elevation or depression. Remember that both of these terms refer to angles that start from a horizontal line, and then angle of elevation elevates its terminal side up, and the angle of depression drops its terminal side down. So we always start from horizontal line, and then we either elevate the second arm or we drop the arm to obtain the angle of depression. But both of them start from a horizontal line. Some rules about notation. The opposite side carries the same name as the vertex. The vertices of a triangle are marked by capital letters, for example A, B, C, and the sides carry the same name but marked by small letters. So for example, this side is opposite to angle A, so it carries the same name, it's a side A. That side is opposite to C, so it carries the name C, and this side is opposite to B, so it is B. Also, we know that the side opposite to the smallest angle is the shortest. So for example, in this triangle, this angle looks like the smallest, therefore the side that is opposite to it, A, is the shortest. The side opposite to the largest angle, in this case it will be the hypotenuse, right, is the longest. And the middle side is opposite to the middle angle. Finally, to solve a triangle means to find all missing angles and sides. So if something is not given, we need to find it. Let's practice. In the first question, we want to solve this triangle. What's given is the hypotenuse, which is 12, and angle A, which is 35. We need to find the side that is marked on this picture as X and the other side Y, as well as angle B. So we may start with finding angle B first, because angle B is complementary to 35. Therefore, it's really easy to get this. It's 90 minus 35, which turns out to be 55, right? Now, to find, for example, the distance x, we can use the definition of one of our trig functions. If we compare x to 12, x over 12, this will be really adjacent to the angle 35 over hypotenuse. So the ratio of adjacent over hypotenuse is called cosine. That's a cosine of 35-degree angle. And now we solve this equation for x. It's enough to multiply both sides of the equation by 12. We obtain x equals 12 cosine 35. And then, using a calculator, we obtain 9.8, rounded to one place value. Finally, we want to figure out how much is y. Again, we can make a comparison of y to the known side, so y over 12. Y over 12, that's opposite over hypotenuse with respect to the angle 35, right? So opposite to the hypotenuse is called sine of the angle 35 degrees. And again, to solve for y, we multiply both sides by 12. So we have 12 sine 35, which turns out to be approximately 6.9. Okay, so we found all three unknowns, the angle, one side, and the other side. Therefore, the triangle is solved. Let's see another example. This time we have given two sides and no angles at all. So first, we can apply Pythagorean theorem, because it's a right angle triangle, to find x. Okay, that would be x squared plus 9 squared equals 15 squared. And solve it for x. Therefore, x is 15 squared is 225 minus this 9 squared, which is 81. And since we want just single x, we need to place square root on the top of it, right? So that becomes root of 144. And we're lucky this time. This is a perfect square number. Root of 144 is 12. Okay, we already found x. Now let's focus on angle alpha, and we can create ratios 9 over 15 or 12 over 15 or 12 over 9. That's up to us. Let's stick with the given data. 9 over 15, that's really adjacent over hypotenuse for angle alpha, therefore it is cosine of alpha. And now to solve for alpha, we need to use shift cosine of that number. Alpha by itself is cosine to the negative 1, which is inverse cosine. This is really undoing the cosine. Okay, so we apply it on 9/15, and we end up with, well, let's see, shift cosine of 9 over 15 equals 53 point, let's round it to one place value, so 53.1. 53.1 degrees. Okay, as soon as we have alpha, beta is complementary, so it's even easier. Angle beta equals 90 degrees minus 53.1 degree. That turns out to be 36.9 degrees. Okay, and the triangle is solved. One more example. Here we have given that angle B is 11.4. We can write it here, 11.4 degrees, this one. Side B, which is across the angle B, is 6 centimeters. We don't know side A and we don't know side C. We also don't know angle A, but that will be easy to get. Angle A, let's start with the easiest part, is complementary to 11.4, so it is 90 minus 11.4 degrees. That turns out to be 78.6 degrees. Okay, one unknown is already found. Now, let's figure out what A is. In order to do that, we need to make a ratio that will involve A and 6. If we are looking for a function of angle 11.4, we should start with 6 over A rather than A over 6, right? Because that will be tangent. opposite over adjacent. So let's set up the equation. 6 over a is the same as tangent of 11.4 degrees, right? Now to solve for a, we need to make sure that a is in the numerator. So the best idea is just to swap these two. A goes up to the other side and tangent 11.4 goes down. So our equation turns out to be 6 over tangent 11.4 equals a. And then using calculator, our a equals to approximately 29.8. One place value is good enough here because that's a side, right? Please check this value on your calculator. Finally, to find c, we can, for example, create a ratio 6 over c. That will be opposite over hypotenuse with respect to the angle 11.4. Okay, let's write it down. 6 over c is the same as sine. Opposite over hypotenuse, it's sine of 11.4. Okay, again, let's swap the c with the sine. Therefore, c will be equal to 6 over sine of 11.4 degrees. Okay, using our calculator, that turns out to be approximately 30.4 centimeters, right? So everything is found, A, C, and the angle A. Next, we have a word problem. From the top of a lighthouse, 41.15 meters high, so on our diagram that will be this distance, 41.15 meters. The angle of depression to a boat is 3.28 degrees. Remember, angle of depression starts from the horizontal line. So that's the line, and we depress the angle by 3.28 degrees. Since we're going to work with this right angle triangle, it will be useful to transfer this angle to the bottom over here. Those are two the same angles because they are alternate angles, right? We have two parallel lines and a transversal, so these two angles are equal. Therefore, we have 328 in the bottom here. Okay, what do we need to find? How far is the boat from the base of the lighthouse? So the boat is here, the base of the lighthouse there. That's the distance that we are after. Okay, since we already have all data placed in this right angle triangle, we have one side given and the opposite angle given. We can create one of the trig ratios that will involve 4115 and x. And which ratio it is of 328? It is opposite over adjacent, so we work with tangent. Tangent of 328 equals 41.15 over x. To solve for x, as before, we swap the x with the tangent. X goes up, tangent goes down. We end up with 41.15 over tangent of 328. And then using our calculator, that turns out to be approximately 718 meters to the nearest meter. So we can give the answer. The boat is 718 meters from the base of the lighthouse. Here we go. Now we have some interesting problem about jet that climbs at an angle of 15 degrees at the speed 362 kilometers per hour. How long will it take to the nearest minute to reach an altitude of 8 kilometers? Altitude really means the height. So let's make a diagram. Let's say this is the ground level and the jet climbs at the angle 15 degrees. At certain time, he is at the height of 8 kilometers, right? So this is our right angle triangle. The question asks us how long will it take for the jet to go from this point to that point. So we're after time. But we know that the time is connected with the rate, which is given here, and the distance that we don't know yet, right? What is the relation between all these three quantities? Well, rate times time, so 362 kilometers per hour times time times the number of hours equals distance. This distance will be in kilometers, right? Because of the denomination here and there. So we would easily find time as soon as we know this distance, okay? Because that will be distance over 362. Therefore, our first goal would be to find the distance. How can we do that? By using trig ratios. For example, if we refer to the angle 15 degrees here, we could use opposite over hypotenuse. So we set up equation 8 over d. That would equal what function of 15 degrees? Yes, it's sine. Opposite over hypotenuse, it's sine of 15 degrees, right? Now to solve for d, again, put the d to the top and the sine to the bottom, to the other side, right? Okay. And then let's use our calculator. That turns out to be approximately 30.9 kilometers. As soon as we have our distance, we can substitute it to the time formula. So it's 30.9 over 362. And that gives us 0.085359. I use a lot of digits because this number is in hours, right? So it's very small and sensitive. Okay, but we need to find the time to the nearest minute. So let's convert this hours into minutes by multiplying by 60. That's minutes over hours, which allows us to reduce the hours, and the answer is really in minutes. Okay, how much is that? That's approximately 5.12, so this many minutes. If we want to be even more exact, we can convert this 0.12 of a minute, multiply by 60, and that will give us 5 minutes 7 seconds. Okay, so we can give the final answer. It will take approximately 5 minutes to reach the altitude of 8 kilometers. Happy flying! And here's our last example. The angle of elevation of the top of a tower is 30 degrees. So, assuming that this is our tower, from certain point, let's say from here, the angle of elevation, this one, is 30 degrees. Another reading taken 100 meters closer to the tower is 60 degrees. Let's use different color. Let's say from here to there, that's 60 degrees when we come closer by 100 meters closer to the tower, right? How tall is the tower? So that's the distance that we are looking for. Let's call it h. This problem can be done in two different ways. Firstly, we can use special triangles because those angles are really special, 30 and 60, right? Secondly, we could pretend that those are any angles. Because what if this question will have, for example, 29 degrees here or 52 degrees there? We need to be able to solve problems like this for any given angles. So let's see the two solutions. Okay, I will record solution 1 here by using special triangles. Since this is right angle and that's 60-degree angle, therefore this angle is 30 degrees, isn't it? On the other hand, if we look at the big triangle, if this is 30 degrees, therefore this full angle is 60 degrees, right? So this one is 30 and this one is 60. We work with two triangles, so it's okay to introduce two variables. One variable is the h. That's the one that we are after. The other distance that would be nice to know is this piece from here to there. Let's call it x. Now, focus on this small triangle. We can extend it to the equilateral triangle somehow like this, right? The green triangle. Then the height of equilateral triangle is the same as half a side times root 3. So we can record the relation between h and x. H is the same as x root 3 from the small golden triangle. On the other hand, using the big purple triangle, well, this is really half of an equilateral triangle if we extend it that way. So this distance, which is x plus 100, is the height of the big equilateral triangle, and this height is also half a side times root 3, so it's h times root 3. Okay, we can create second equation, x plus 100 equals half a side, which is h, times root 3. So now we have system of two equations, and we can solve it for x. It's enough to substitute the h from the first equation, this one, to the second equation over here. We end up with x plus 100 equals, instead of h, we have x root 3 times another root 3. So altogether is just 3x. Minus this x, we get 2x. Therefore, x by itself is just 50. 100 divided by 2, it's 50. So we already know this distance. This distance is 50. But we are after the height of the tower. Therefore, let's go back to our substitution, and the height of the tower is x, which is 50, root 3. That's exact answer. That's our height in meters. Okay, now let's see the solution without the use of special triangles. Again, we'll introduce this variable x as before, this distance over here, and we are going to set up a system of two equations. One equation for each triangle. Starting with the small triangle, we can say the ratio of h over x is the same as tangent of 60 degrees, tangent 60. And the second equation comes from the big triangle, the purple one. Again, opposite h over the hypotenuse, which is x plus 100, h over x plus 100 equals tangent of this angle, tangent of 30. Okay, that's our system of equations, and we just need to solve it. Notice that this time we don't rely on special angles. Those can be any angles. We'll find the values of tangents on a calculator and round them to 4 decimal places. Okay, so this will be equivalent to, let's solve each equation for h. So in the top we have h equals tangent 60, which is 1.7321 when rounded to 4 places, times x. And from the bottom equation we have h equals tangent 30, which is 0.5774 when rounded to 4 places, times the whole denominator x plus 100. Okay, here's our system of equations. Now, since this is h and also that is h, we can compare them and create one single equation. That would be 1.7321x equals this much. In the meantime, we're going to distribute over this bracket, right? So it will be 0.5774x plus 100 times this number, it's 57.74. Just moving the decimal dot 2 places. Next step would be to collect all x's, so it's this number minus that number. Let's use our calculator. That becomes 1.1547 of x equals 57.74, and x by itself is 57.74 divided by 1.1547, which turns out to be approximately 50. There is a small decimal after 50, but this is because of rounding the tangent values before, right? So yes, we've got the same answer, x is 50, and as before we need to use this to find h. So when we substitute to the first equation, h becomes 1.7321 times 50, which is approximately 86.6 meters. Notice that 50 root 3 is exactly the same as 86.6 when rounded to one decimal place. So yes, that agrees. And our answer is the tower is approximately 86.6 meters tall. So here are the two solutions. If someone can make use of special triangles to make it a little bit faster, that's great. Otherwise, this method always works, and it works for any angle.